right, so welcome back, chat. We just did this one. Sorry, Basil. The video died, but we're retrying. This is a 45, 45, 90. Now, if we want to use the shortcuts, which you should know, we can. How do I go from a leg to here? You multiply by root 2. So this is 5 root 2 up here. Now, I can do the sine, cosine, tangent, and everything from this angle all the same. Opposite over hypotenuse is 5 over 5 root 2. But here's what I'm suggesting. If we know this is 45 degrees, but this isn't on the unit circle, is there a 45-degree triangle on my unit circle? And what is the y value there for sine? So whether we use the unit circle or we use our triangle shortcuts, we get the same answer. There's value to the unit circle unless you want to use the shortcuts all the time. I don't think you do for every single triangle ever, so let's just get these. Cosine at 45 degrees. Root 2 over 2, and this is the only one of the few that I can do confidently in my head. 1. Okay, we are going to do one more little extension. If this is 30, and you don't have to add this, we're going to summarize this. If that's a 30-degree angle on this blue triangle, what's this one? So quick question for you. What is the cosine of 60 degrees? And you can look at this triangle, or you can look at the unit circle, but I want to notice something. It's 1/2? Hold on here. This is the same as the cosine of 60? Okay, well, let's try that again. What's the sine of 30? What? Huh. Interesting. The cosine of 60 is the same thing as the sine of 30? And then the cosine of 30 is the same thing as the... Whoa. Yeah. That's what you were wedding. Yeah. I thought you were wedding the math fact, which I was much more psyched about. The cosine of 30 degrees is the same as the sine of 60 degrees. I don't know why I'm holding that there. We're going to go one more random one. Do not give me a number, okay? I just want you to tell me what is the same as the sine of 41 degrees. It's the cosine of something. And using only what we've done right here. Say it again. 49. Why? I agree.
Because they looked at it, so they right angle.
Love it. We're going to clean up the language, but your idea's there. You got it. Is there anything special relationship-wise between 30 degrees and 60 degrees? They are complementary. What's the one if they add up to 180? Supplementary. How do you keep them straight in your head? That's how I do it. C and S alphabetically and 90 and 180 numerically. Or it's always right to complement somebody is the other way that it's typically produced. Okay, now looking at this. From just these, what we have here is a special relationship. Now, it's not going to address everything, but it's kind of annoying that sine matches up with cosecant and stuff, right? Like that part's whatever. But do you realize that for every function, sine, tangent, and secant, there is also a cofunction that exists? And that language shouldn't, like, it might sound kind of scary, but check it out. What do you think is the cofunction of sine? Cosine. What do you think is the cofunction of tangent? Cotangent. And the cofunction of secant? Cosecant. And real quickly, what are the first two letters of complement? C-O. Oh my gosh, it's like they're just these ratios that are with complements of my sine, my secant, or my tangent. So we're going to get out our very first of what we're going to call our identities. So we're going to have a weird transition here today. We're in the same section, and I usually use pink to think, so I'm going to change color, but it's still going to be identities. We're going to start in just a few minutes talking about our trig identities, at least the first of them. Now, one of the coolest things that we get to do in here for a little tiny bit, they're way different than we saw before, but just remind me, what was everybody's very most favorite part of geometry? Now, the theorems themselves aren't that cool, but it's what we do to theorems. We prove them. We will be doing proofs in here. Okay, full disclosure, they are not 2-column proofs. Second, full disclosure, I've seen all of you guys write successful proofs in the past. You can groan, that's okay, but you're fine. You can do them. Okay, we're gonna start talking about identities. Now, for our purposes, we do have some identities that just showed up for the very, very first time. The identities that we have just found just now, and we're only going to see some basic ones now, but we just worked out, at least by example, what we call the co-function identities. So identities, they're true for everything, and we get a few co-functions right now. Okay, if we want to be very rigorous, and we're going to start being more and more rigorous as we go, we're going to let theta have, and we just need another letter to name another angle. We could name it alpha, beta, gamma, delta. Delta? It's a weird choice, but I'm okay with it. A lowercase delta looks like a music note, so I'm going to draw a really big one. This is a delta. I do it like this. That's a delta. Let theta have delta as its complement. Okay, so weird choice only because delta is typically used to represent a really small, like a lowercase delta is just a really small change in x compared to just a regular change like capital delta. But that's okay, it works, it's a Greek letter. Theta and delta are complements. That's where we just wound up. Now, there's a few ways we can write these. If I write a function, the sine of theta, the co-function identities tell me, well, that is the same as if I were to evaluate the cosine of, and we have two different ways that we can write this. Because we defined it, what's the complement of theta right now? This will always be true. A function, the sine, how do I want to word this? The trig function of an angle is equal to the cofunction of its complement, which is kind of ugly to say. There is an alternative way that we could write this, and instead of having two different angles, if you really hate this delta, that's okay. We could say instead that the sine of theta is equal to, and I'm going to take a 30-second pause to this side. If theta were 40 degrees, how would you find its complement? Not what is its complement, but how would you find it? You would just say its complement would be some unknown for now, right? And it equals 90, and then you would just subtract it. So the way that we could do this, if you don't want to have to use two different letters, we could say the sine of theta is the exact same thing as the cosine of 90 minus theta, 90 degrees minus theta, if we're doing degrees. We could do the exact same thing in radians, and instead of 90 degrees, what would we write? Pi halves minus theta. Now, for each of our three trig functions that aren't co, we could have a similar statement. Out of curiosity, we'll just commit to it. Are we going to use alt theta and delta, or do you want to use just theta? Which one do you prefer, or does it not matter to you? Okay, this is the one that's more commonly presented, but I like to see it in other ways. Help me out with this statement. Give me another non-co function. We have sine and cosine. Tangent. What do you think we would do if we're doing it in this format? The tangent of theta is equal to the cotangent of what? What's the complement of theta? You could say delta, I heard that, but Matilda is also correct. You could say it's 90 degrees minus theta. There's one more waiting for us. Sine and cosine, tangent and cotangent. The secant of theta is going to be equal to what? The cosecant of 90 minus theta, or pi halves. Now, we're not going to write them all, but I do want to make sure that we can see it. A function, and it's so awkward to word. The sine of an angle, I'm really struggling to come up with a wording for this. I'm just going to write it. I'm going to show you guys that we don't really have to write them all, okay? Check it out. What if I said, what's the same as a cosine of theta? And you can write this, but you don't have to. It's the sine of what? Good. So we could switch it around, right? We can do it both directions, whether I'm saying the sine and its cosine or the cosine and its sine. As long as we have the complement, it works. Okay, class decision time. I can give you a short assignment now to work on for a bit, and then we can continue talking about identities. Or we can continue talking about identities, and I can give you a single assignment instead of two different assignments. Do you want a little time to work now, or do you want to just keep getting some new stuff now? Let's see where we're at. Let's work for like 15 minutes and just see how it's going. If there's issues, then we'll address those issues. If we're doing well, then maybe we'll finish it in that amount of time. Okay, homework for the next few minutes, at least. We'll call this homework 4.3.1, and it is waiting for us on page 286, I believe. And let's see. I want you guys to do 1 through 3. They're vocab. And let's see here. Is this stuff easy or hard? It's kind of hard. Okay. 9 through 25 odd. Cool. I'm going to give you guys like 15 minutes. I'm going to step outside here to grab something in just a second. Do you want the vocab word real quick? Our daily vocab. You want to learn a new word real quick?
Yeah.
All right. Basil, if you're watching this, you tell me when you get to class after watching this video. So hopefully Friday you're feeling better and in class. But if you get to class and you tell me that, Holloway, your favorite color is green and your favorite number is number 7, you will get a piece of candy when it arrives. If Basil doesn't tell me this, you guys all get a piece of candy when it arrives.
That's actually funny.
Here's the other deal. You are not allowed to text Basil and say Holloway was gone. There's no video. Like, we want her to watch the video. Don't burn somebody else's thing for a 10-cent piece of candy. Cool.